Hello students, this is Dr. NITRATION, your chemistry mentor, welcoming you for an important session in phenols. Today we are going to see the chemical properties of phenols. Actually, the chemical reactions of phenol can be categorized into two. One is the reactions involving the OH group and the next one is the reactions involving the aromatic ring. So today we are going to see the reactions or the important reactions involving the aromatic ring. Okay. Actually, this phenol undergoes electrophilic substitution reactions. The reason is the OH group present in the phenol is an ortho-para directing group and it directs the incoming group to the ortho and the para position. Okay. So therefore, this phenol undergoes electrophilic substitutions at ortho position and as well as in the para position with respect to OH. Moreover, this OH group is an activating group and it activates the ring at ortho and para position towards the electrophilic substitution reactions. Okay, so this is why these phenols undergo the common electrophilic substitution reactions much more readily than that of benzene. Okay, so now we are going to see some important electrophilic substitution reactions and other reactions characteristics of phenols. Okay, so the first one is the halogenation. See, these phenols when treated with excess of bromine water gives 2,4,6-tribromophenol. Okay, so this phenol undergoes halogenation readily to form the polyhalogen derivatives. Okay, that's why it's giving 2,4,6-tribromophenol. What's happening here? Here we are having 6 bromines, is it not? So 3 of the bromines will be taking up 3 hydrogen atoms from here and it forms HBr. Okay. So 3 HBr. So rest of the bromine atoms will be getting attached to the ortho and the para position of this phenol. Okay. So here one, here one, here one. Okay. So that's the reason why we are getting the 2,4,6-tribromophenol. See, here we are making use of aqueous media. Okay. So along with this bromine we are having the aqueous media, right? On using this water as a solvent, this phenol gets oxidized to phenoxide ion because this water is a polar solvent. Okay, so what's happening here is this phenoxide ion is more reactive than phenol towards electrophilic substitution reaction. Hence, on using this aqueous solution of halogens, polyhalogen derivatives are obtained. Can you understand? See, if you want monohalogen derivatives, then this monohalogen derivatives can be prepared by when phenol is treated with bromine dissolved in carbon disulfide at 243 Kelvin. Okay, so when this phenol is treated with bromine in the presence of carbon disulfide at 243 Kelvin, we will be getting a mixture of ortho para bromophenols. Okay, so let me write the product now. Ortho product OH. So here we are having the ortho product and the next one is the para product. Okay, OH Br. See here, this is a minor one and this is a major product. Okay, can you understand? So what's the difference between these two here? This water is a polar solvent whereas this carbon disulfide is a non-polar solvent. That's why we are able to get this ortho and the para product. Whereas, see, if you are using a polar solvent, you'll be getting this type of product. Can you understand? We'll be getting the polyhalogen. Understood? So the next very important reaction is the nitration. See, when phenol is treated with dilute nitric acid at 293 Kelvin gives a mixture of ortho and para nitrophenol. Okay, see, when this OH group is present in the phenol activates the ring to such an extent that the phenols can be nitrated even in the dilute nitric acid at a low temperature. That's why we are able to get the ortho para product. Okay, so NO2. Okay, so here this is the ortho nitrophenol and the next product is para nitrophenol. Okay, NO2 OH. Okay, so this is a para nitrophenol. See, when nitration of phenol is carried out in the presence of nitric acid and also in the presence of concentrated sulfuric acid, we will be getting 2,4,6-trinitrophenol, which is commonly known as picric acid. Okay, this is commonly known as picric acid. So we will be getting 2,4,6-trinitrophenol OH NO2 NO2 NO2. Can you understand? So this is called as a picric acid or the 2,4,6-trinitrophenol. Actually, however, the yield of this product, that is picric acid, in the above this reaction is low. This is due to the oxidation of phenol by nitric acid used in the reaction. So therefore the picric acid is usually prepared in an indirect method. Okay, so how it is prepared in the indirect method? In order to prepare picric acid, phenol is first heated with concentrated sulfuric acid at 373 Kelvin. When a mixture of ortho phenol sulfonic acid and paraphenol sulfonic acid is obtained. Next mixture is then heated with nitric acid, okay, which will be giving the picric acid in and that will be a good yield. Can you understand? The next very important reaction is Kolbes Schmidt reaction. See here, the phenols when treated with sodium hydroxide gives sodium phenoxide first. Okay, so first we will be getting sodium phenoxide. This sodium phenoxide, which on heating with carbon dioxide at 400 Kelvin and 4 to 7 atmospheric pressure, a carboxyl group is introduced at ortho position and sodium salicylate is obtained as a major product. This on acidification yields salicylic acid. Can you understand? See here, let me explain now. This is a phenol, is it not? This is phenol, which on treatment with sodium hydroxide gives a sodium phenoxide. Okay. ONA. How this is formed? This hydrogen combines with OH and water is removed, okay, H2O. So we are getting sodium phenoxide. So this is a sodium phenoxide. Now this sodium phenoxide, which when treated with carbon dioxide at 400 Kelvin and 4 to 7 atmospheric pressure, okay, this when treated with carbon dioxide at 400 Kelvin between 4 to 7 atmospheric pressure, will be getting a carboxyl group is introduced. Okay, so here first what happens is the carboxyl group will be introduced here itself. Okay, COONA. This undergoes a rearrangement. Okay, this undergoes a rearrangement and this carboxyl group will be getting shifted to the ortho position. This carboxyl group will be shifting to the ortho position. Okay, so this will be the product, intermediate product. So what happens here, the hydrogen which is present here in this position will be getting shifted here and here will be getting COONA. So a rearrangement takes place. Okay, rearrangement taking place between these two. Okay, now what's happening here, when acidified, when this is acidified, will be giving salicylic acid. Okay, OH, COOH, salicylic acid. So this will be taking place in the presence of an acid. Okay, right? So this is what happening. So we'll be getting a salicylic acid. So this is called as salicylic acid. So this is a very important reaction. Next important reaction is Reimer Timann reaction. Phenols when treated with chloroform in the presence of aqueous sodium hydroxide at 340 Kelvin followed by hydrolysis gives salicylaldehyde. So this is a chloroform. So when this phenol is treated with chloroform in the presence of aqueous sodium hydroxide at 340 Kelvin followed by hydrolysis will be giving an aldehyde. Okay, so we'll see what's happening here. See here what's happening. This OH will be getting combining with this hydrogen and there will be a removal of water molecule. Okay, there will be a removal of water molecule so that this Na will be getting added up to this one. Okay, so we'll have this product ONA. Then again what happens is one of the chlorine atom from CHCl3 will be getting added up with the hydrogen here so that there will be a removal of HCl. Okay, minus HCl. Understood? So that we'll get the product again. This CHCl2 will be getting added up to this one. So here CHCl2. Understood? Now what's happening here? This again when treated with sodium hydroxide NaOH. Okay, so when it is treated with sodium hydroxide, again there will be removal of 2Cl. Okay, so we'll have this chlorine and this side sodium will be getting removed as 2 NaCl. So rest of 2 OH will be getting added up here. So we'll get the product like this ONA. Here we'll have CHOH OH. Okay, now again there will be a removal of water molecule. Okay, so we'll get the product salicylaldehyde. Okay, here we'll have CHO. When this is treated with dilute HCl, finally we'll have OH here and CHO. Okay, CHO aldehyde mean there will be a removal of NaCl. Okay, so finally we will be getting salicylaldehyde. So this is salicylaldehyde. Okay, next important reaction is coupling reaction with weakly alkaline solution of benzene diazonium chloride at 273 Kelvin to 278 Kelvin. Para hydroxyazobenzen is obtained. Okay, so this is benzene diazonium chloride. Two azo groups are here. So benzene diazonium chloride, when it is treated with the phenol, what's happening in the presence of an alkaline medium, sodium hydroxide at 273 to 278 Kelvin. Here this chlorine from benzene diazonium chloride and hydrogen from the phenol will be removed as HCl. Okay, so HCl will be removed. When HCl is removed, this nitrogen will be getting attached to this benzene ring. Okay, so finally we'll get the product like this. This gets attached to the phenol. Okay, so what's this? This is para hydroxy. It is in the para position. Hydroxy group is in the para position, is it not? So para hydroxyazobenzen. Okay, oxidation of phenol with chromic acid produces a conjugated diketone known as benzoquinone in the presence of air. Okay, phenols are slowly oxidized to dark colored mixtures containing quinones. So this is a sodium dichromate. Sodium dichromate in the presence of sulfuric acid, it gives chromic acid. So when this phenol, when it is oxidized in the presence of chromic acid, we get benzoquinone. Okay, we get benzoquinone. Double bond O, double bond O. So we'll be getting benzoquinone. Okay, so the name of this compound is benzoquinone. The next important reaction is sulphonation. Phenols can be sulphonated at ortho and para position by the action of concentrated sulfuric acid. Ortho isomer predominates at lower temperature while the para isomer predominates at higher temperature. Ortho isomer will be getting predominated at the lower temperature and para product will be getting para product at higher temperature. Okay, so let me write the product now. At higher temperature we will be getting the para product, that is paraphenol sulfonic acid. Okay, so this compound is called as, it's in the sulfonic acid group is in the para position, so paraphenol sulfonic acid. Okay, so when 293 Kelvin, when this phenol is treated with concentrated sulfuric acid, we will get an ortho product. Okay, the ortho product will be getting predominated, so SO3H. Okay, orthosulfonic acid. Okay, orthophenol sulfonic acid, and obviously this orthophenol sulfuric acid is the major product. Okay, this is the major product and this is the minor product. Understood? So next important reaction is a condensation reaction. See, when phenol is condensed with phthalic anhydride in the presence of concentrated sulfuric acid, phenolphthalein is obtained. See here, this is a phthalic anhydride. When this phthalic anhydride is treated with phenol, 2 molecules of phenol, there will be removal of water molecule. Okay. Okay, and finally we'll get the product, that is phenolphthalein. C double bond O, C, this one gets connected, and here we have the phenol ring because water molecule is removed, is it not? So here we have the OH, and here again another phenolic group. Okay, so this is a phenolphthalein. the product is phenolphthalein. Understood? So we'll get phenolphthalein when phenol is condensed with phthalic anhydride in the presence of concentrated sulfuric acid. Okay, that is reduction. Phenols when hydrogenated in the presence of nickel between 473 to 533 Kelvin, it gives a cyclohexanol. Okay, so we are having 6 hydrogen atoms. See here, when it is hydrogenated, this hydrogen gets attached to all these double bonded carbon atoms, and finally we'll get the saturated product, that is a cyclohexanol. Okay, OH. This is a cyclohexanol. Understood? This reaction, see here, this phenol undergoes Friedel Craft's alkaline and acylation reaction in the presence of anhydrous aluminum chloride to give a mixture of ortho and para derivatives. Okay, usually the para derivatives predominates in general. Okay, in general the yield will be very poor because aluminum chloride used in this reaction coordinates with the oxygen atom of the OH group. Okay, that's the reason. Okay, so para derivatives will be getting predominated. Now here let me write the reaction. What's happening? Phenol, when it is treated with methyl chloride. Okay, when it is treated with methyl chloride in the presence of anhydrous aluminum chloride, this product is formed. Okay, hydrogen from here will be getting reacted. See, this will be removed. HCl will be removed. HCl will be removed, and we'll get OH CH3. See, this is orthocresol. Okay, this is orthocresol, and also we'll be getting the para product. Okay, at times we'll have this also, we'll get para product. So this is paracresol. Okay, so but this will be the major product. As I told you earlier, this will be the major product. So what's happening in the case of acylation? See here, this phenol gets it is reacting with acetyl chloride. Okay, so here the same type of reaction is taking place, and finally we'll get this product OH COCH3, ortho acetyl phenol, orthoacetyl phenol, and also a para product will get OH, here COCH3. So what's the name of this compound? Para acetyl phenol. Okay, well, fine students, I hope you might have understood what I have taught today. Let me meet you with another important topic in my next session.